Well, I'm going to change my title a little bit. Well, last week when I sit down and try to put together this talk, I realized that what I wrote there in the abstract won't work, because this is supposed to be a dialogue between geoscientists and mathematicians. And I have too much respect for mathematicians to bore you through the nitty-gritty details of lithospheric dynamics and faulting. So I'm going to, how do I move this? All right, so I was trying to struggle. I struggled a little bit. I'm trying to find out what to talk to you. The mathematicians are very smart people, and I have a problem talking to smart people. Okay, so when I was struggling, I saw this diagram on the, I really need something here. This one, okay? This is, I saw this figure, and I decided maybe that's a good place to start. Another figure is finite angles match for a 3D model of Asian continent, and to give you a orientation here. Another part of this is parallel to this map here. So we can find and the idea for this model is trying to understand the driving force for the diffuse deformation in Asian continent. And this model was set up by one of my Chinese colleagues, a young scientist who has a PhD in applied mathematics. And so I thought that's where we can start this conversation. Because in this model, he built a lot of details, all the horizons, and not only that, it's a 3D model, so we also put in all the vertical variations of lithology and associated physical parameters. My concern here is that with so much variations in the model, can we really understand the driving force, the cause for the deformation in Asian continent? Many of these parameters are not very constrained. So sometimes maybe you have too much detail. And that's why I'm very happy for this morning's talk. Although I did not expertise and search models, but I get a sense that we deal with very similar problems in geosciences. Geosciences traditionally is observational science, so data collection is a major driving force. And we have geophysicists, geochemists, everybody seems to have their own models. Now with increasing amount of data, their model become more and more sophisticated. For example, you have technologists together seismic wave structures of the lithosphere of the mantle. So you have a model, which means a spatial variations of seismic velocity, which you relate to different rocks. And because you have all these details, you are excited. Many of you want models to put all that details in the numerical model, okay? Because all these details spend millions of dollars in Canada. You want that to be represented, and you want us to use those details to understand, give you a better answer of how Earth works. So, as you are asking for a modeling, and actually most of the time you are asking for a simulation. These two words, at least in geoscience literature, are used as interchangeable. But there's maybe some difference. Because when you say a simulation, you really want the numerical models to reproduce all the details that you have seen in your observations and then give some explanations. But for modelers, I would argue that most of the time I would have to say I can't use all these details because once I put all these details, I don't know what I'm doing. I don't know what I'm getting. I don't know what comes what. the best thing I can do is perhaps do some modeling. That means I try to understand the basic physics of working humanities. So let me give you a couple of examples here. Because I studied with the Tibetan Plateau and Asian tectonics, and maybe we can start from here, because it's part of my model building process. And here is the Tibetan Plateau, the largest model built on Earth today. And the geological history is that the Tibetan Plateau is mainly built by collision between the Indian continent and the Eurasian continent in the past 50 million years. If you hold a Eurasian continent fixed, you will see India has been moving northward at a rate of 50 millimeters per year. How this continental collision built or produced this multiphysics and affected lithosphere deformation in the surrounding regions in Central Eastern Asia has been a major problem in geodynamics or continental tectonics. Because you can say we can do computer simulations or modeling to see how this process works. But if you take a closer look, you realize that this is not going to be an easy job because the lithosphere is very, very complicated. Of course, you can also argue that the magnetic core is also complicated, but no, we can't see that. Lithosphere is right here. We see a lot of variations. There are faults everywhere, and there are different blocks of lithosphere with very different ethology or different blocks like geology. So, how are we going to do that? Well, one approach is taken here by visual distinction model. And although this model says basically argues that, look, the lithosphere is about 100 kilometers thick. We are talking about a region of thousands of kilometers across. So, with that kind of aspect ratio, I don't really have to worry about the details of the vertical variations. I can treat the continents as a thin sheet. And also because we are talking about a process that works over millions of years, I don't have to worry about all the details of faulting because over this time scale, as a whole, the continents roughly behave as a viscous fluid. Okay? So I can just use a thin viscous fluid and have a region indented as India to push through into the Asian continent to see what happens. And in such simplification, this model captures some important features of this collision of tectonics. One thing you can see that, well, these are the thickened layers. So one thing this model says is that the collision is mainly accommodated by crustal thickening. And that explains why the crustal thickness in Tibetan Plateau is roughly twice as thick as the surrounding regions. Also, this model predicted that this thickening process propagated gradually from south northward, and that seems consistent with a lot of geological record that shows how the lithosphere deformation started in the celluloid as a consequence of this region. So sometimes, I would say many times, the best model is the simplest because it captures the basic physics. But, okay, so this is another simple model. This model is an analog model. Here, this bridge, a piston, is India. It is pushed into a plasticine Asian continent. And the result is that this collision squeezes off blocks of Asian continent. Okay? Along this fault, we call the strike slip faults. And I read this paper when I was a graduate student, published in 82, but gave me a very deep impression because you can see a lot of these features in this simple model that you can correlate to the geological features that we see in Asia. The opening of South China Sea, the strike slip motions, all that. But these two models have very different implications for Asian tectonics. In the first model, the essential model, it says that most of the collision and the shortening of the crust has been accommodated by thickening, and not the process produced or formed the Tibetan plateau. But if you are studying in Southeastern Asia or Eastern China or Central Asia, you don't see much of this effect until very geologically recently. But if it's this model, then the collision will have a far-reaching and immediate impact on everywhere in Central East Asia. Every part where once this collide, you will start feeling it. Okay? And for a long time, there is a debate between what's the major mechanism that accommodates the Indo-Asian continental collision. One model says basically is crustal thickening, another model says is natural extrusion. But you can see from this model that all this is built in the model. The first model does not have plastic geology, does not have faults. It cannot simulate the strike faults that we see in geology. The second model is a plant-free model. It does not allow thickening. So there is no thickening factor produced from this process. Everything squeezed in has to be squeezed out. Okay? So useful models, but it has limitations, and we done a little bit of modifications of this essential model. So this is a 3D finite angle simulations. Simulation of this essential model, but we have the vertical variations, so that allows we have a positive flow, and we have a boundary force built in there. I will see you with details. So this is a time series simulation of the collision that caused the formation of Tibetan plateau. And this is the two profiles you can compare with the produced topography with observed ones. With this model, we can see the time-dependent partitioning between crustal thickening and natural extrusion. And this basically says at the beginning, this curve says at the beginning, most of the shortening of the crust was observed by thickening and mountain building, but gradually this part reached a limit, and more of this shortening or collision has been accommodated by natural extrusion, and that's why today, with the Asian tectonics, you will see a very clear patterns of natural motions of crustal material. Okay, so at this point, I can put in my personal prejudice here, because Earth is very complicated. No matter how sophisticated our models are, it's a very broad simplification of nature. So with that, if you reproduce all the details of nature, I would say something is wrong. But on the other hand, we should also remember that while we have a supermodel that shows us some useful physics, that's great, but we have to remember that it also has limitations. And we're illustrating this point more with another example. And I want to thank Dave for talking about earthquakes that set the stage for this. So this is Geosciences And that's what the cause of all the earthquakes in California, including this 1906 San Francisco earthquake. After this earthquake, Harry Reid proposed a model for how earthquake works. It's called an elastic rebound model. Okay? So you have two blocks of the crust that moves against the fault. On the fault surface, on the fault plans, it becomes static, so it cannot move. And here, some stress will build up. And here, at some point, too much stress, it will break through the fault plan and produce an earthquake. Okay. So, in the past 100 years, this is probably the best aspect of earthquakes we understand. And a very useful, very influential model that's the foundation for a lot of earthquake studies. So we are, because this understanding of how earthquake works, we spend a lot of time trying to measure how stress is accumulating. Well, we can't really directly see stress very well. So most time we try to measure how strain is accumulating and try to study the earthquake history. And once we have big earthquake, we think that the stress is released, and in the process, gradually stress will build up again, and here it goes to the next earthquake. So if everything works ideally, we will have perfect cycles of stress build up and the displacement. Every time we have earthquake, we have a major displacement, stress is released, and another cycle of earthquake comes. And these cycles of earthquake, I don't know if you went to yesterday's talk, I suppose said about this, also in the hazard analysis. This is information for every aspect of earthquake studies. Without these cycles, without these recurrence intervals, we can't really assess how dangerous, how much risk we have in the future. But this model has its limitations as well. As Dave showed in his line of arguments, some patterns are even in the best behaved sites of as we expected based on understanding of the cyclic earthquakes. And here I'm showing a numerical simulation this time. I still don't have all the details there. I simply set up a model with a fault that has the first order geometry of the Shan geothermal. I don't even consider the heterogeneities of the rocks. I'm just assuming that I have all the same strengths. So with all the cells, I'm just simulating when randomly one cell ruptures the perturbed stress on the neighboring segments, and sometimes they go very long, sometimes go short, and we don't know exactly what to control this. So this, in these figures, a few panels, the white segments are the simulated ruptures or major earthquakes. And the one major feature you can see is that they all stay there, rupture again and again after some time. These rupture segments migrate along the Shan geothermal. Sometimes it's big, which means a bigger earthquake. Sometimes short means a shorter earthquake. So if it behaves this way, then we have more difficult time to do the earthquake predictions or forecasting. And this bunch of figures are the stress, the simulated stress evolution. Each line is one selected point on one segment of the fault. And in the general pattern, if you look at this segment here, you see there is looks like a pattern. After some time, one segment, all these points have a rupture or stress drop. At the same time, and that means a bigger earthquake. And this one have a pattern. Some segment is very random, does not show a very clear pattern of the earthquake or rupture. So since can be very complicated, and in this kind of simulation, we cannot reproduce the earthquake history, but at least we can be aware that nature can work in a much more complicated way than we think. So the third part, or the next part I'm talking about, this is the one in the abstract. I want to say a few words about the challenge of modeling faults, and perhaps mathematicians can provide more guidance here or advice, because faults are very difficult to model in geodynamics. Computational geodynamics is based on continuum mechanics. You have faults there, that's a problem. You have to come up with all kinds of ways to treat the faults. Not only that, but the faults behaves changes at a different time scale and different spatial scale. At this different time and spatial scale, different physics is going on there. And we have lots of this very different geology. And Earth has a system that is very complex. And typically in a tectonic setting, we have many faults that may interact with each other in a way that we don't really understand. So let me just, how much time do I have? 5 minutes? So let me go through very quickly here. So for example, if you look at the geological on a scale map, and this geological is simple line, one simple line. If you take a closer look, you can see a lot of faults here. Okay? And I'm picking up these two faults here, the southern part of the geological and this part of the southern. We can pick up because the southern part of the is a problem that as much as falsely as the geological or low geological is usually and what you say you are, we are interested in this because we have these big ones, it's also California is big. That's the first thing. Structure, most part of the channel years ago, and it's a lot hard. It's structure. But there's a number of things you can that's an effect. Right? You can look at other four segments because our earthquake happens in the perturbative stress here. So if you are a nearby fault line, you will see both the shear stress and normal stress change. An increase of shear stress or a decrease of normal stress will all make the fall easier to see. Okay? So that's showing as the red current here, and this diagram basically says that the past earthquakes, about 9 moderate-sized earthquakes in the past 20 years on the San fault may have reduced the common stress on the Geosciences fault, therefore delayed perhaps its rupture. Well, this is only one process working here. Another process is that we have two faults here that collectively accommodate emerging motion. While one fault is ruptured a lot, another guy can be easier life. While another fault is locked, the other faults will be loading fault. So this diagram here is simulating the synthetic earthquakes. Even in a simple model, it comes with clusters, not regular space events. So you can compare with a cluster period with a quiet period. And here we are looking at the loading rate on the southern Geosciences fault by just looking at what happens on San fault. But San fault If low means low earthquakes or low major ruptures, the shear drift flow is loaded much higher than the average degree shown by the red here. But on the other hand, if the sun snowfall is producing a lot of earthquakes, the loading rate on the shear drift flow is lower than the average. So the line is easier there. And let me jump over this. On a longer term, the faults will also interact and cause initiation of new faults. For example, this bending of the shear drift flow called the big bend formed about 5 million years ago. And when this bend formed, it concentrates plastic strain along this part. And that's what Eastern California shear zone, and today is producing a lot of earthquakes and accommodate about 25% of the relative plane motions. So, and different time scales, different physics are working here. Okay, I come to the last part, few slides. So, now talking about the challenges. Well, in the past few years of past decade, we see a lot of new opportunities. One, of course, is the computing power, both the hardware and algorithms. A lot of things we did not think about, I did not think about until a few years ago, about 10 years ago, in the first class, Windows class, I can play, I can use parent computing to play new games. On the other hand, we have a lot of dynamism. Some of you probably heard the first of a major research initiative in the US, in Geosciences, that is producing a lot of data. So the problem now is, what are we going to do with this? Sometimes we need more data. Many times we are flooded with data. We don't know exactly how to make sense of this. Okay? So there are different approaches. For example, this is one approach. Okay? And this actually is a numerical representation of finite elements mesh showing topography in southwestern China. Another part is the fault. Which fault in 2008 it produced a 7.9 earthquake and killed about 90,000 people. Okay? So one approach is to make the model more realistic. You have all the faults built in here, or you can have more. But that's column stress, those column layer, we are talking about less than 1 Pascal change caused by earthquakes. And each of these kinks, these geometric variations of fault, can easily cause much higher, 10 orders of magnitude higher stress change there. So having all these details may not help. Of course, another way is to say, well, maybe with all these resources, we can try to understand new physics. So I'd like to show this figure yesterday, but this cartoon here is one example. I want to say that maybe with your help, with all these resources, computing power and data, we can try to understand new physics. Because of the top right one here is showing a plate boundary form. And as they showed earlier today, most of the earthquakes happen on plate boundaries where two tectonic plates, giant plates, are moving at a constant rate. That rate has not changed in the past few million years. So because that kind of constant loading, we can expect first earthquake happen, later second earthquake will be some kind of periodic behavior. But once you go to near continents, like Central Eastern Asia, Central Eastern US, where some of you heard about Geosciences now. Here we don't have relative plane motion to load any of these faults. Rather, we have a system of very complex faults collectively accommodating tectonic loading. And one fault may rupture, produce earthquake, and then go sleep for long time. Next time earthquake is for other faults. How we understand this complex system for interaction seems one good example that the new computing powers, the new data, and help for mathematicians can help us understand new physics. I will stop it. Thank you.
How do you load your faults in your models? What happens below the seismogenic zone?
In the channel geosciences, for example, is loaded on site by imposed relative plane motion.
What's below the dribble layer? Is it viscoelastic cut space, or you have zones?
It's viscoelastic. Right, it's a viscoelastic layer, but with fault it's a plastic, so it's the bottom part is we know the whole side. So crust and the viscous layer. Because we don't know how to I know there is a different loading. You can have the lower crust of the viscous layer flows and not with loading.
So the long-term interseismic strain accumulation is a product of past earthquake history, or it's a product of the
It's both. By earthquake history, you note the viscous layer, and then it has in the post-elastic process, the viscoelastic relaxation process.
Again, just wearing my geoscientist hat for the mathematicians, I'd like to say that you didn't mention this, but there's a lot of interest in phenomena that happen on micro and even on nanoscales as being initiators of the spontaneous formation of these faults. I mean, there's a major distinction between brittle rupture and fluid associated rupture. And this is in some sense analogous to the fact that in climate, I mean, a lot of the phenomena that are perceived as being very important are associated with clouds and cloud radiation interaction. And those are also, eventually happening at microscales, the cloud nucleation, CCNs, I can't remember what they stand for. They have the nucleation of these clouds and so on. So it's really not clear to which extent, I mean, there has been some talk of stochastic parametrization, and unfortunately, ambient carry west in the same path. It's not clear that there is a terribly good way that we know, mathematically or physically or whatever, how to deal with these phenomena, which are not just one or two scales below the ones that we're mainly interested in, but quite several orders of magnitude below. So, maybe there's some new mathematics needed there.
There's a lot of studies in language. I'm trying to show a spectrum of timescale and different amount of physics. One in language is the integration process. The earthquake study, of course, there are a lot of studies from lab experiments or to the earthquake phenomenon, trying to understand the nucleation, the spontaneous nucleation process, and when the studies therefore, what I do related to forecasts or the value, the change of p values shows perhaps stressing levels. That is more difficult for what I'm showing here. I'm sorry, because it's hard to observe.
Yeah, I want to make a comment in a similar vein that observations show that faults do tend to organize earthquake occurrence, but not all earthquakes occur on the major faults. And in fact, it can't, because there are compatibility conditions to plate motion that basically require faults to evolve and to grow. And some may shut down, as you mentioned. And I think there's really a role for mathematicians to help understand the fractal geometry that provides some sort of self-consistent picture of deformation that helps inform how earthquakes occur and what their fracture surfaces are, which are slightly different in almost every case from the faults. So there's some really good mathematical problems there, and I think that's a really fruitful area of collaboration.
Well, there are fascinating laboratory experiments that show self-organization, microfaults into major ones, and you know, on the mathematical side, what is missing, I mean, there's a lot known about self-organization and so on, but not in the absence, I mean, not in the presence of heterogeneity. You know, the fact that there are large-scale constraints which constrain the self-organization of the small scales. That's an interesting area.
So going back to your very nice review of the Himalayan uplift problem and these two classical models as to how the uplift is accommodated, what do we have available in terms of data and the variation through space over the plateau of vertical motion from GPS arrays?
The vertical motion is very hard. As you probably know, the GPS is good at horizontal motions, but order of magnitude for vertical motions. I know there's just a recently organized a funded project to study, but I haven't seen GPS results for the vertical motion yet.
Well, I mean, the GPS is quite good for vertical motion if you have a long enough time series, and you know if the installations are permanent. So
that's relatively right. It's horizontal is still much better than vertical.
Yeah, sure, but you know the vertical motion measurements are. You know.
Especially most of these measurements so far are continuum scale measurements.
Well, this is why I say. I mean, if there were reasonable coverage of the plateau with permanent installations, it would be very, very interesting to see the heterogeneity in the vertical motion.
Right. There are some leveling studies, but you know the leveling are not scale.
And what you say is true not only in Himalaya, but almost any mountain range.
Yeah, absolutely.
But that's the problem for mountain building studies. Anywhere we don't have very good constraints on the rate of current update. And most of the geological data are many proxies. You know, for example, you look at fishing track. That tells you erosion, not really tell you the update.
No, and the good data that we have are usually well displaced from the regions of maximum uplift. I mean, in the Peruvian Andes, for example, along the coast, we have beautiful records based on relative sea level observations of the uplift at the coast, but we don't know much about the rate of uplift in the inland.
Well, the problem is it's been a chicken and egg thing that because you're talking about a decade of measurements, funding agencies, you know, we've tried repeatedly to get, for example, funding to do that in the Andes, in the Altiplano process. Because it's a decade, you know, the funding agency has trouble getting its head around the decade.
Well, we're getting killed in basically all areas of earth science by the, how shall I say, the inhibition of the funding agencies to commit to long-term scale.
Yeah, I mean, we like 10 years ago, we've been pretty clear simulations that 10 years we could be in a sub-millimeter in the Andes in vertical. And I gather the same in the service. And as you know, we've been unable to get more vertical. It's not vertical, is, you know, it just doesn't fit in its mindset if you want an answer in 3 years.
No, you need a decade.
Yeah, a decade.
Just interrupt a second, because we have more discussions. I asked actually all the speakers to come up. So the idea now is that we have some discussion with all the speakers, and then at 5:15 there's a